Hi everyone, welcome. How's the energy level today morning? So, so we dropped the assignment 2 if you have seen the notifications, just to make sure that you guys are not bored. I'm sure after submitting assignment 1, everyone was really bored and wanted to do something, so assignment 2 is already there. So assignment 2 this year, it's a revamped version, so hope you had a chance to check it out. But I think today's lecture is very pertinent to the assignment because today I'll cover the main chunk of the transformer main portion that is also in the assignment. So the idea was that, like, you know, today I can talk about the abstract matters, but I think doing it in code will actually give you a very good idea of understanding of the underlying mechanics. And yeah, so let's get started. So assignment 2 is posted. I talked about it, and the office hours now are going to be in person today after the class. And this is the marking scheme for assignment 2. The shaded part on the top is essentially what I plan to talk about today. Is it a little bit, maybe it's a little bit too small, but at a high level, you know, there's the evaluation, blue score. So I think the bottom part is the easiest part of the assignment. You should just start with that and get it out of the way. It's independent, you calculate the blue score. We talked about in the last class. And the decoding gradient beam search, I find from experience, I know that the greedy beam search part is the one that usually takes the longest or the most confusing part, I don't know, implementation wise. So, but we talked about this. So today we're just going to go over the building blocks of transformer and the architectural components. And yeah. So these are the two great TAs for the head TAs for this assignment, and this is the email address. Please use this email address for any assignment 2 related questions. Oh, this slide is actually, this picture is from last year's Reddit. I found it so funny that I decided to just copy it over here. Can I see by a show of hands how many undergrads are here in the room? Okay. Okay, cool. So it's like 50-50 mix. So, so I mean, the challenging part of this course is this, that I know that some grad students were taking this course in the past. Like, these are very easy for them. Like, they have done internships, they have worked on language models and stuff. For them, it's very easy. But on the other side of the spectrum, there's second-year students, third-year students are taking it for the first time, and they found like some tasks to be daunting. So it's always a task of sort of trying to manage that, keeping that in head, keeping that in my mind. So I found that a little bit challenging for this course. But anyway, if you're an undergrad and if you're feeling like, if this figure is not funny to you, then talk to me. Okay. So today what I wanted to do is, yeah, so just going to do a recap and then the focus will be on the building blocks and components, and I've tried to design the slides in a way so that it just corresponds or aligns with the assignment as well. And then after that, I'll talk about some of the variants or popular transformer structures and briefly talk about one sort of popular model for each, from each architecture family. We'll look at BART, and then an encoder decoder model like T5, and then decoder only model like GPT. And then next lecture, this lecture will seamlessly segue into the next lecture, which is on large language models, where we'll talk about large language model stuff, which are built on top of this transformer architecture. Okay? So this is just a recall slide from last slide. The paper that introduced the transformer architecture, it's in the required reading. Please read the paper. It's a good paper to read. And the motivations of transformers. So we talked about RNNs, and then we talked about how we could use RNN-based architectures to do machine translation, and then we are now switching to transformer. And the main idea was we talked about the advantages of this architecture, like parallelizability and you know, efficiency and taking out the recurrence essentially. And a few other pros of it. I think we talked about it, but yeah, just a recall slide for you. So the only thing I want to talk about, I wanted to emphasize in the slide is that remember that the encoder-decoder architecture, we're not doing anything to it. So the encoder-decoder sequence-to-sequence idea will persist in transformer architecture as well. So you have the encoder and decoder. We have seen this in the machine from a machine translation or a language modeling perspective. And then in transformers, we'll use the same paradigm, but we'll just instead of the inner workings, we'll just get rid of the recurrence and use attention-based blocks. At a high level, transformers is just identical blocks stacked on top of each other. So here on the right hand side, you can see this architecture, very well-known architecture from the paper itself. And on the left hand side is the same architecture without all the bells and whistles. So this is if you abstract away all the bells and whistles, these are the modular blocks that are used, that are just stacked up. So on the encoder side, we have a stack of like 6 identical blocks on top of each other. And on the decoder side, we also have like stack of 6 identical blocks. And the inner blocks inside each of these blocks are sublayers. So if you consider this as one encoder sublayer, and then it consists of 2 sublayers, FFN, which is feed-forward network, and a self-attention layer. And on the decoder side, we just have the same thing, but we have another layer called cross-attention. Otherwise, these represents the sublayers. So if we talk about, let's say, feed-forward network in the encoder part first, then the same idea applies to the decoder FFN. They're the identical layers, right? Sublayer. Then, so the way we'll do is like we'll talk about each of the sublayers, and then in the decoder part, we'll only talk about cross-attention and the difference in self-attention, like what does the masking do, okay? And the rest of it is already will be discussed in the encoder block. So if you look at the main components, you have the attention mechanisms. There's some, we'll talk about the single head attention, and then multi-head attention will be the same idea, but we've talked about multi-head attention. And then self-attention, cross-attention, and masked attention. So the cross-attention is just the attention between the decoder and the encoder. And the masked attention is the same as the self-attention, but we apply this for the decoder case, we mask it so that decoder doesn't get to see the future tokens, right? And then the bottom 4 are basically the other sublayers, like the feed-forward MLPs. And then layer normalization, positional encodings, and residual connections. So these are, the bottom 3 are the bells and whistles. So let's set up like a plan for today's discussion. So first I'm going to talk about attention mechanism. And like anything else, before introducing, yes, question? Yeah, so the cross-attention, remember from the NMT lecture, we talked about a high-level architecture of transformers. So you have the encoder and the decoder, and whatever the input embeddings are coming, like they first do self-attention with each other, and then after some time, they do cross-attention, which means encoder-decoder attention. So then you're doing encoder to decoder attention, which is similar to the attention that we saw earlier with seek-to-seek plus attention. So you have an encoder, like the token embeddings, you have the decoder token embeddings. And then remember in seek-to-seek attention, we do the attention between the encoder and decoder. So cross-attention, or also known as encoder-decoder attention, is just that attention, okay? So in a way, cross-attention is something that you have already seen in seek-to-seek plus attention. The self-attention is something that's new in transformers that we haven't seen.
So what would happen if you didn't have cross-attention? How did we solve the problem before having that? I'm just trying to understand the incremental value.
Yeah, sure. So think about like, the machine translation task or the language modeling task, right? So, so the encoder is first encoding the French sentences, right? And the decoder's job is to output English sentences. So if you're not joining them, like how does the decoder get any information? Yeah, so same thing in the SIG to SIG plus attention. What did you do? You had the encoder, and the decoder at each time step was looking at all the tokens that was encoded by the encoder, and then it was conditioning on that, and then it provide the output. So cross attention is exactly the same thing. Yeah? Okay. So for everyone, the question was essentially what's the difference between cross attention and self attention. But we'll talk about it, and I find that before any technical concept, I just want to do like an intuition that sort of helps to stick the ideas. So I find this as a very apt analogy, and I'll come back to this when we answered the exact same question that he asked about cross attention. So if we were not, as humans, if you don't have any technology, if you have like, let's say the echoing system, which essentially stores three kinds of information: your personal information, your academic information, and your financial information. So if you didn't have any computers or anything, how would you store that? Like filing cabinet, right? We have to go back to filing cabinet. And how does the filing cabinet work? Even if you have you usually have like a label on each of the drawers, right? Where you store that kind of information. So the same thing, so that if we have this three kind of information and we want to store this in a filing cabinet, then we'd have those three labels and we'd have three drawers, and for each student, like we'll look up, if it's a personal question. So everyone knows how a filing cabinet works, so I'm not gonna go on about it. And then inside the drawer, you'd have some documents that are related to each of these labels, right? So let's say those labels or the drawer labels are our keys, and whatever's inside each of the drawers are like values, the actual documents. And then when you encounter a query from anyone, whether it's a student or some other institution, the questions are like, it could be, there's three examples of each type of question. Okay, so what's the current academic standing, current financial stuff. So as a human, if you encounter any of these questions, the first thing you're going to do is like you're going to go to the filing cabinet, you're going to open that drawer that corresponds to the category, and then look for the values inside the values which one you want, right? So these are our queries. So if you think about like this, then transformer attention, the query key value, the QKV, you can think of it in these terms. So the first thing when you get a query, you'll find like as a human, how do you decide which drawer you have to open? You find the similarity, right? What is the query? What is the student's residency status in Canada? That's a personal question. So you have three labels. Then you're like, okay, so it's a personal question, I'm going to go open the personal drawer. So that's it. So in your mind, you're doing some kind of similarity measure, right? Between the question and the labels of the drawer. Simple. And so, yeah, so you do some kind of similarity measure in Transformers case, let's say dot product attention. And then once you open it, and then inside the drawer, you try to find within the values, like what. So you pay attention to the documents within that drawer, okay? So yeah, that is sort of the analogy of the attention mechanism in Transformers. Does that make sense? Yeah. So the question is, what is this root decay? So this is just a scaling parameter to normalize the values. So essentially, it's a constant to reduce variation or just like normalize the value of query key. So the term is called scale dot product attention. So if you just do Q and K, that's dot product, right? And when you just add this scaling parameter, it's scale dot product attention. It's just a constant. So yeah, the question is that why is it specifically root D? So D is the dimension of your key vector, okay? And the reason why we use that, I have to talk about like, statistics here, because the variance sort of scales with the dimension of your key vector. But in short, we just normalize it by the square root of the dimension of the key, okay? All right, so first, let's focus on the encoder part. And I said that we'll cover the identical materials in both encoder and decoder, and then we'll go to decoder and we'll only talk about the differences. So, so I think a good idea would be to first get rid of the bells and whistles. So as I said, that this one is just a sublayer only block. This is an abstraction. This is just, each of the encoder blocks have a feed-forward network and a multi-head self-attention. So these are the two sublayers. But this doesn't have there's so many bells and whistles, so we have a little bit more. So if you look closer into this, then we see that this block, besides the sublayer, there's some bells and whistles, which are the residual connections. And there's the layer norm. And we also have the positional encodings. Now, the positional encodings and the concept we already talked about in the previous lecture. So why do we need positional encodings, how we can do it? And basically, so this is going to be on the very top. In this slide, I'm going to use this as our rolling example. So we have the French sentence, mini tutorial de transformer, which is like, I think the gazillionth transformer tutorial. I don't think the world needs another transformer tutorial, but here I am. And the English translation is tiny transformer tutorial, okay? So with this running example, on the bottom right, you can see that at a granular level, you have the French sentences, the tokens that are coming in, you have the embeddings, and then you add the positional encodings, and then that is being fed to it. So as a plan, what I'll do is like first get rid of the bells and whistles, which are the residual connections, the layer norm, and then I'm going to talk about attention, the sublayers, the attention sublayer and the feed-forward sublayers, and the positional encoding slides are also there, but I don't think we'll be spending too much time on it. Does that make sense? Any questions? Okay, so residual connections. So the residual connections, the concept is from computer vision. Everyone knows the ResNet architecture. So the main, it basically transformed the depth and the performance on ImageNet, I think. So the idea is very simple. Deep layers are bad at mapping the identity functions. So you're basically like attaching a residual connection to the output of each of the layers. So if you look on the top right-hand side, so the main idea of residual connection is this. So if you have whatever your input is from your layer embeddings, you just add back that raw embeddings to the output of the layer. Okay? Yeah.
How is this related to skip connections?
This is connected to too many different things, and so what do you mean skip connections, right? Like
Skip connections, the problem is that with the CNNs, we have like
yeah,
gradients,
yeah.
and then you have like basically like a highway of information at the top, so that they're grading different payments.
Yeah, so this is, yeah, I see, yeah. It's really, I mean, yeah, you can think of it that way, and you can also think about, remember in LSTM, I like to think of it more of like information. Are you familiar with like the transformer circuits or circuit kind of representation? So the idea is that, so if you think of this residual connection, right, and if you straighten it out and move all this, like whatever sublayers on a side, then it's like a straight line going from your original input, and everything else is basically adding to it. So it's the same connections, but it's just a like different ideation, which is similar to like in LSTMs, we had like a C, which is the long-term history context, and you're basically like recursing on that. You're maintaining a long chain. So the residual connection sort of helps to propagate this information so that you don't lose the gradients. And another thing is that it also some papers show that like it smoothens the curvature, so backprop is a little bit more efficient. So it's good for training. Yeah. So in the transformer context, that equation on the top right becomes our x prime s is sublayer, whatever sublayer xs plus the raw embeddings of xs itself. Okay, so which is denoted by the yellow xs over here highlighted. Any questions? Residual connections? Okay, so then we have layer normalizations. Layer normalization is simply normalizing the embeddings so that we remove the variance, we only keep the useful stuff. So this, what happens is like we basically calculate the mean. So you have your embeddings. You have think of like the layers mean, and then you just normalize it to 0 mean and 1 standard deviation. Basic normalization technique, and yeah. So the connections are, one thing to notice is that the connections are after our residual block. So this is called post-layer normalization, which is the default transformer architecture. Okay, so you have the input coming in excess, it goes through the sublayer, you apply this residual connection, and then whatever the output is, this HL, you feed it to for layer normalization. After it's normalized, you take the HL prime and then continue, then feed it to the next sublayer, which goes through, there's a residual connection, and then there's again layer normalization. So the idea is that the layer normalization happens after the residual blocks. So this is known as post-layer normalization. Any questions? Do you have any question? No? Okay. And a variant to the post-layer normalization is pre-layer normalization, which is shown on the right-hand side. And the main difference is now we do the layer normalization within the residual block before passing it to the sublayer. Okay? So what advantage do we get out of it? With the post-layer normalization, in transformer training, we have to do like a few warm-up steps at initialization. So the learning rates, we don't change or anything. How do you usually do like learning rate change when you're training a model? What you do is like your learning rate is gradually annealed or decreased, but in post-layer normalization and default transformer training, you'd basically keep it like there's some warm-up steps required. And the reason is because initially, if you do post-layer normalization, think of this sublayer over here, multi-head attention. So the input is going through a sublayer, and after the output, there's no normalization. So anything like, think of it as the value being changed. There can be some extreme values, etc. And that is added to the residual block, and that is passed to the layer normalization. So we're not normalizing for, basically in pre-layer normalization, we're saying that we'll normalize the input embeddings first and then feed it to the sublayer blocks. And the advantage is basically it gives more stable initialization. And it also allows removing any warm-up stage from training, so it's more efficient training-wise. But other than that, like similar concept, the goal is to do the same thing, to normalize, remove the uninformative information, okay? All right, so now we've talked about layer normalization residual blocks. Now I want to talk about the self-attention. So the self-attention block is highlighted over here with the red block. And so again, our setup is this. We have an input block for a sentence, and the output is English translated sentence, and ET is the reference sentence. We have 3 weight matrices for query, key, and values. And the attention mechanism is the same thing, but we are self-attention, meaning that we're attending to the same, we're not doing, there's no, the source and target both are the input sentence. So this FS is paying attention to itself, okay? And the attention steps or recipe stays the same as we have seen before, 4 steps. So attention between the query and key, so calculate the query and key score. So first you calculate the query key value for each token. How do we do that? We use our weight parameters for each of Q, K, V. And then we calculate the attention score between the query and keys. And then we normalize the attention scores by applying softmax and then take a weighted sum. So the high level steps for attention, as we have seen in SIG to SIG, stays the same. So the first step, for each of the tokens, we calculate the query key QKV values, okay? Second step, we calculate the score between query and K. And third step, we normalize. And fourth step, we take the weighted sum. Exactly same steps. I think the only thing that's different is in step 1, where you're just calculating the query key, QKV values. But other than that, it's the same thing. If we represent this in a vectorized notation, same thing, it looks like something like this, okay? Same 4 steps. Trying to see who looks very confused. No one is? Okay. All right, let's move on. Multi-headed attention, as we talked about this in lecture 5. It's the same idea. You just you know, project the heads or the matrices or the vectors into a shrunk space. You calculate it for n number of heads and you join them back together. There's nothing new to this from what we have already talked about, and I think I did a little bit of code demo as well. But yeah, this is exactly the same idea. So you calculate, you have n heads, you calculate the tension exactly in the same way in the previous slide for each of the heads, and then you, at the end, you concatenate all the head values together and just project it through a linear mapper or weight matrix like W output, let's say, parameter matrix. And that's your value that you pass along the chain to the next sublayer or output, whatever it is. And yeah, I mean, there are usually some questions that are mostly related with understanding the dimensionality of input outputs, etc. But I think those are best answered if you actually code it out and see it for yourself than you know, trying to understand it from paper if you have any confusion. But at a high level, the idea is the same. Okay, any questions? Okay, feed-forward layers. So conceptually, what does the tension do, if you think about it? So the tension is doing, it's just reweighting the value vectors in a way that you're passing, you're doing some linear mapping. But how do you learn? In order to learn, you need to have activation function, right? So the feed-forward layers are just simple MLP layers that are there for that. So we apply non-linearities or activations to enable the learning. So each feed-forward sublayer consists of two identical feed-forward MLP layers. Just two layers, simple feed-forward layers, okay? What it's doing is denoted by this equation over here. So you have two linear layers, you have corresponding two weight matrices, you're just basically passing it through a ReLU, and then it's just what a simple feed-forward network does, and then you're outputting the values. Yeah, so each, the feed-forward sublayer is applied to each of the token positions separately and identically, and besides that, there's nothing to it. Any questions with feed-forward layers? Okay. So then we have the positional encoding part. Recall from slide lecture 5, neural machine translation. Yes? Oh, okay. So recall that why we need the positional encoding, because attention by itself does not infuse any word order information. So we need to have a notion of positions of the word tokens. And the way we do this is by adding some oscillating, like sinusoids to each dimension position, and yeah. And then we slap the positional encoding on top of the embeddings. You can also concatenate it, but people tend to add it. And whatever output you get, you feed that to the encoder block. Yeah.
So the two things here. How do you, like, taking a step back, I know that, for example, in recommendation algorithms, you do a lot of like sine and cosine encoding to basically track the cyclical components that happen over time. So, for example, like holidays, like seasonality, stuff like that.
Temporal, yeah.
Things like day of the week, like month of the year, for example. Things that matter, but maybe things like the second doesn't really matter that much, right? How do you choose that like month of the year and like day of the week type of features to encode that like cyclicality?
Yeah.
In a task like translation.
Yeah. So for everyone, I think the question was how. So the question was about, like, you know, the cyclicality of whatever the embedding that we're infusing to infuse the word order. Now, the thing that you're talking about in recommendation system, which is also identical to, like, let's say time series forecasting and whatnot, where you have to keep a notion of temporal relationship, right? So here's the same idea, but the difference is that here our time frame is just the length of the sequence. So all we're trying to do is say, so here are like from, so if you abstract away that sequence length is S or T, right? So let's say our sequence level is S, and we're saying that we're taking S steps, or we have S days, we have S seconds, whatever it is. That's the only thing we care about. But the idea is that we're embedding the notion of position. So if you abstract that away, and don't go, like in time series forecasting, what you're doing is that you're also encoding the time using the sinusoids. So this guy over here. So you said that how do you delineate between
like periods, like basically like what are meaningful periods?
Yeah. So the positions. So for let's say days, right? So days, if you want you because every in the encoding the position every day, this is different, right? So the year would be a 365 word sentence, right? So where each of them is one day, which is the position. So it will be different. But if you're saying that, how do you infuse? So that gives you a temporal relationship. So if you infuse that information, then you can say that day 120 comes after day 7. Do you agree with me?
I mean, what I understand is like a year is very obvious that it's like a period.
Yes.
Right, that it's like in one sense over.
Right.
But it's like in a sense it's not that obvious, like what happens in advance, right? Unless like for example like a dot would be good for like a sentence, and then maybe you could like normalize that to be like kind of like a year, or like and then a paragraph, or like that could be like a month and then like a paragraph like a year or something.
Mm-hmm.
And then days would be like tokens, right? So it's like what I'm trying to understand is like
So.
how do you find those?
Right, but you're trying to compare apples to oranges, right? So because so you're trying to say how do I understand between day and month, but you have to embed like something different. Here, this embedding is just for the temporal sequences of whatever you decide to abstract as your token is. It's just saying that like the order between whatever the tokens, that can be days and years. But your question is more about like, but then how do I know what is a year and what is the day? But that's a separate question, right? So in that case, you'd probably have a different like added some kind of function that delineates between day and year or month. Anyway, we're digressing from our topic over here. But the idea is that like for each position, you have a different embedding that sort of infuses the notion of the order in the sequence. We can also talk offline about this, like because I can talk about time series forecasting and how do we do that in time series forecasting, but it's not the right place. Okay, so we have. So the check marks are items that we have talked about so far, and the only thing remaining is now the decoder. And in the decoder, we're not going to repeat the same sublayer blocks. So I'm not going to talk about the decoder's feed-forward network because it's the same block, sublayer block. I'm only going to talk about the things that are nuanced in the decoder, which is the masked self-attention and the cross-attention piece, which is between encoder and decoder attention. Okay. So masked self-attention, the goal or the reason for masking the self-attention is so that the decoder doesn't get to cheat. So in a task like machine translation, first of all, the output embeddings are shifted by 1. The way we do this is by introducing like a start token or a special token, right? The same idea in the sig-to-sig attention. And decoder at any time step should not be able to see what it has to predict next. So in the decoder, we're doing self-attention, but we're limiting our attention to only the tokens that the decoder is allowed to see at a time step. Okay, so yeah, we're calculating, let's say, between attention query and key. We'll be using a look-ahead mask, and the mask is essentially sets the values the decoder can't look at to negative infinity. And when you say negative infinity and then you take a softmax, like they're basically like you can view them. And this is what drives it. So it's basically saying that, if keys that are, it can only look at keys that are less than the step I'm on. Otherwise, it's negative infinity. let's look at this from our running example, okay? So let's say we are now the decoder, and now we're trying to translate the English sentence, and this is our reference sentence, tiny transformer model. And so the bottom left-hand side diagram is just, if you rotate it to the left by 90 degrees, you can get this. It is offset by 1 by introducing this start token. Output embeddings are usually offset. And then you can see that if you take the x-axis to be I, the query values, so if you're at I equals to 1, then it can only look at values that are less than 1 on the y-axis, so it can only look at the start token. If you are at tutorial, then you can look at all the values less than 3, so transformer tiny s, which is reflected on the y-axis, so you can look at transformer tiny and s. So that's basically like, that's the idea. So any questions about this? Everyone is like 100% clear on the concept? If you are, then I have a question. So there's no questions, so everyone's clear. And so my question is this: why is the top row on this figure, why is the top row different in the top row over here? What's the difference? So here, this is it's denoted, the query axis is denoted as AQ, right? So if you flip it, you can see that this top row is different than so my question is, why is the top row different than first column over here? They're the same thing, right? I can see that here, all negatives here, there's a 0 here. What's the difference? Yeah?
Is that to the fact that the attention score itself is a transpose?
No. Cool. So the concept is not clear. All right, I'll let you figure it out. Yeah. Rotate the matrix and think what can, yeah. Yeah, so it's very simple actually, because in this case we're not doing any shifting, output embedding shifting by start token, right? So the only difference is that we're shifting the output token embedding by 1 over here on the top case. On the bottom case we're not. Anyway, moving on to encoder decoder cross attention. So this is the same attention that we actually did in the SIG-to-SIG attention, and we talked about it a little bit in the beginning of the class with the question, using the notations as we have done before. So at this stage, both the encoder and decoder has done self-attention with its own whatever input it had, and then now it's ready to do cross attention between the encoder and decoder. Now here I find that the example that the analogy that gave in the beginning, the filing cabinet analogy. So in a transformer, the keys and values come from the encoder. It's also called the memory. And we do attention with the KV, we do the attention between the queries and keys. So the query comes from the decoder. And we get the decoder query by, we have our decoders weight parameters for Q, we get our QI, and the tension is between the decoder's query and the encoder's key. Otherwise, besides this caveat, it's exactly the same thing. So intuitively, it's basically the decoder is trying to decode something, like the English sentence. So it has a query, and it will ask the encoder that, what am I translating? And the encoder is basically, has the values, and it will basically answer to that question. So you're doing the query key attention, and once you have found out, after doing the query key attention, you have found out that where should I look for the values, The encoder then looks for the values V, and then you do the query key attention times the V to get you the attention score. Okay, so I think this covers the block we started with for the assignment. Yeah, so you'll do the layer normalization. Multi-head attention, feed-forward layer, and then you have some components from each of the blocks we talked about. The encoder sublayer, we have normalization. One thing we have is we have the post and pre-layer normalization, and so that you can do an analysis as to what is the difference of using, or it's the advantage or disadvantage of using each kind of layer normalization. And the decoder, same thing, but with masked attention, and yeah, that's pretty much it. And then you have to implement the padding mask to create that the masked attention. Okay. All right. So if there are no more questions, then I'm going to just talk about some of the language models before we segue into large language models. At this time, the period that I'm going to talk about, like the BARTologies or BART-based model, they're usually say that's pre-trained language models. So the delineation is done between LLM and PLM. So PLMs are the period where, from post-transformer, you had a whole bunch of language models like BART, which are in the range of still not crazy, billions of parameters. It's basically relatively large comparatively, but not super large. So we'll talk about some of those models, and then in the LLM lecture, we'll talk about the different features of very large language models that we see today. In terms of the architectural variations, so one thing about this language models are that, architecturally, they all have the same blocks. Sorry, do you have a question? Do you have a question? Okay. You can, if you have to talk, then please go outside. Thank you. Architecturally, the transformer, underlying architecture is transformer blocks, but as we have seen or talked about, is some of them just has encoder block. And then we have some architectures that has just the decoder block, like the GPT series. And then we have the encoder decoder blocks. Even if you look at papers that are the newer language models coming in, if you look at the paper, the architectural variation is very little. The differences comes from the language, the data that they're trained on, right? So the corpus they're trained on are some minute, for example, the attention span and things like that. But fundamentally, it's amazing how this transformer architecture it's basically based on the same architecture. So I'm talking about let's say Llama, or even in the GPT models, that they're very simple architecture, but mostly driven by the data, and then there's also a mixture of experts, I guess. And the third kind of architecture is the encoder decoder, where you have the original transformer structure with some bells and whistles. Yeah, so these are the three variants. Yeah, this is a very old benchmark snapshot where these PLMs were kind of beating all kinds of at that time standard benchmarks of LLM language tasks, NLP tasks. And the BART, we talked about it at a very high level, but I'll do a little bit detailed explanation of BART. So this was a landmark language model. It was a ubiquitous baseline in NLP for some time. So the idea was that first you do pre-training using the masked language modeling objective. And after that, so this is encoder only, and then you do fine tuning on whatever NLP tasks that you're trying to solve. Yeah, architecturally, it's basically like the encoder block of the transformer. So here in the picture on the left, you have encoder only, and the OpenAI GPT is decoder only, and this is the Elmo model we talked about for contextual embeddings. So this slide is just the language modeling objective, right? So instead of doing the encoder, we have seen the cross entropy laws being backpropagated in an encoder decoder architecture for language modeling. Here, what we do is we do at a high level denoising objective. So you take sentences, you block some of those pieces out, and then at the probability distribution, you basically try to calculate that the loss based on how you have filled in the blanks. And yeah, so this is also called a transducer model in a way, because every time step or every token you have probability distribution output. Yeah, and this slide essentially talks about a little bit more details of how the masked LM objective is actually trained. They use two. There's another task next sentence prediction, but later on, later research showed that removing this task didn't really affect the performance of the language model. And then there's a lot of papers and research regarding, what are, there are some questions about, we have multiple heads, but what are each head doing and things like that. So it turns out that there are certain patterns that each of these heads capture. And so the advantage of having multi-head detention, like it says that usually BART base has 12 heads, or it just says that what each of the heads, what are the patterns of it. There are later research showing that, for example, the Stenny et al. BART rediscovers the classical NLP pipeline 2019 paper, and I was told by one of the TAs of the course that he had a later work which refutes it, and it's in the website if you're interested in taking a look. It says, does BART rediscover the classical NLP pipeline? So yeah, but you can read more about it in the papers if you're interested, but this is from 2019. Some limitations, well, word knowledge. So yeah, this is some of the limitations of this kind of models. Because of time, I'm just gonna, you can read it. There's nothing hard to understand from the slide. I wanted to talk about T5, but I think I'll punt that to the next lecture. But the idea of T5 is you have an encoder-decoder model. This causal attention mask, so causal with prefix. So causal attention mask is also the masked self-attention that we saw. The causal with prefix, the main caveat is, so before we were saying that the decoder only can see what came before it, right? What preceded it. Now, like in the causal with prefix or prefix language model, we say that x1 to x3 are prefix, and the decoder can start decoding with this knowledge. So think about it. So let's say if you want to say that translate this sentence, and the task is defined by the first few tokens, translate this sentence. So the decoder starts with that prefix, and then it starts decoding. So then like the decoder's knowledge of this, you can think of it as like some task description or something, right? So so that's the main difference. So then it starts, and from here onwards is the same pattern that you cannot see the next token it's going to generate. So that's causal with prefix. So it also does the denoising training objective, where in BART you are corrupting, let's say, one word token, but in this case you're corrupting whole spans. So this is an example of, let's say, English to German translation, and that is good. To das ist gut. In the training case, you can see that you are masking for inviting with a special token, same with last, so you're corrupting spans, and your targets are also like spans. Yeah, and here at the bottom you can see that there's some, for prediction, the model is fed prefix, and as I said that in the prefix you can feed some kind of task specification. So translate English to German, and when it's decoding it starts with this prefix knowledge. And let's say we take another NLP task, MNLI, for entailment prediction. So you're infusing it, the decoder, MNLI premise, it already starts with that knowledge. So what I'm about to generate is for this task. Okay, so that's how the prefix attention comes into play. Okay, so yeah, let's stop over here, and then next lecture we'll talk about the GPT series and then the large language models.